In this lesson, we're going to be looking at characteristics of polynomial functions. Polynomial functions can be written in standard form. The linear function, f of x equals ax plus b, it's a degree 1, even though you don't see the 1 there. Quadratic function is f of x equals ax squared plus bx plus c, which is a degree 2. Cubic function, f of x equals ax cubed plus bx squared plus cx plus d. And it's a degree 3. It says the equations of 9 polynomial functions are given below. Use technology to draw the graph of each function. Note the characteristics of each graph. We did this in the previous lesson. If you want more practice, go ahead and do that. But I gave you a page in class that has more than 9 on here. Now, I've organized these graphs according to what degree they are. So we've got the linear functions first, then the quadratic functions, and then our cubic functions. In general, we can see that linear functions are straight lines, quadratic functions are U-shaped or parabolas, and then our cubic functions are the new ones we haven't looked at before, but they're sort of S-shaped. Okay, so it's important that you're able to, just by looking at the graph, identify what shape it is and which type of function it is. It's also good to know what degree that is associated with. On the reverse hand, if you look at the equation of the graph, you should automatically know what shape it is. There's other characteristics that we can figure out just from looking at the equation of the function as well. Let's fill this in our notes. So this is on the next page here. It says, investigate. How would you describe the shapes of different polynomial graphs? Well, the graph of a polynomial function is continuous. This means that the graph has no breaks. You could sketch the graph without lifting your pencil from the paper. We just talked about a linear graph being a line, quadratic being U-shaped or a parabola, and a cubic function being S-shaped. Now, all of our functions have a constant term. How is that constant term related to the y-intercept? So let's go back and look at our page again. I'm going to be flipping back and forth between our notes on that page, so make sure you have it handy. And if we look at, all of them have a constant. So -6, -2, 12. This one's got 36. So what's in common with all of those? Well, the constant doesn't have an x value. So if we let x equal to 0, all you'd be left with all of these functions is that y value. And that y value is your y-intercept. By definition, that's what a y-intercept is. Okay, so let's fill that in. So the constant is the y-intercept, and that's because we let x equal to 0. Now it says for number 3, how does the sign of the leading coefficient affect the end behavior of the graph? Well, end behavior, remember, that's how the graph rises or falls, and what quadrant it's starting in and what quadrant it ends in. So let's go back and look at our page here. So the leading coefficient is the coefficient in front of the variable that determines what degree this is. So for our linear graphs here, we're just going to look at graphs 1 and 2 because graph 3 is a constant, right? If we look at this one, our leading coefficient is 1/2. This one is -5. Okay, well, if it's positive or if it's negative, it definitely affects our graph. Here we're going from quadrant 3, right? Here we're going from quadrant 3 to quadrant 1. When my leading coefficient's positive. When my leading coefficient's negative, I'm going from quadrant 2 to quadrant 4. So it makes a difference, right? Here I'm rising to the right. Here I'm falling to the right. Well, that's just with linear graphs. Is that the same when I do quadratics? Well, here this one's negative, and the other two are positive. It's a positive 1, and this is a positive 1. Well, for the positive ones, again, I'm going up and to the right, but for the negative one, I'm going down and to the left. Well, that's the same pattern. Is it the same for cubic functions, and you might predict that yes, it is. So here's my -1, here's another -1. Okay, so for the two negative ones, they're going down and to the right. And if I'm going to look at my two positive ones, they're going up and to the right. So we can draw a conclusion here, right? Summarize what's going on. If the leading coefficient of the polynomial function is positive, the graph rises to the right. If the leading coefficient is negative, then the graph falls to the right. Here we have that summarized in the first part of number 3. In the second part, it says when the degree n of a polynomial is odd, the graph has opposite behavior to the left and right. If the leading coefficient is positive, then the graph falls to the left, rises to the right. If the leading coefficient is negative, then the graph rises to the left, falls to the right. So what exactly are we talking about here? They're saying that if it's an odd function, not odd as in like funny looking, but odd as in 1, 3, 5, 7, right? In this case, we're just talking about our linear and cubic, because the leading coefficient, or sorry, the leading term tells us the degree, right? A degree 1 or a degree 3. If it's even, like a quadratic, the degree is even, that would be like x squared, x to the power 4, x to the power 6, and so on. That's what we're talking about here. Okay? So we don't really need to talk about the quadratic up here. We're going to talk about it down here. But it says when it's odd, the arms are opposite. So that's talking about the cubic function linear, and you can see that one arm is up and the other arm is down, regardless of which way it's facing. Whereas with the even, like our quadratic, the arms are the same. So either both up or both down. Talking about when we're talking about even, we're talking about the degree. So it says when the degree n of a polynomial is even, then the graph has the same behavior to the left and to the right. If you look at our cards, you can see that all of our quadratics either have both arms up or both arms down, whereas with our linear, not the constant one, but these ones, one arm's up, one arm's down, and the same with the cubic, one arm up, one arm down. So that's more information that we don't even need to graph. We can see that that's going to occur automatically just by looking at the equation of the function. Now if we look at our linear functions here, how many x-intercepts do they have? Well, if this one has 1, this one has 1, and this one has none. Okay, so 1, 1, and none. What about for our quadratic? Well, this one has 2. This one has none. And the third one has 1. We're counting x-intercepts. Cubic function, this one has 1. This one has 1, 2, 3. This one has 2. And if you look really carefully here, this actually doesn't touch. So this one only has 1. So the next question we're asked is, how is the degree of a polynomial function related to the x-intercepts? Well, linear functions can either have 1 or none, and it's a degree 1. Quadratic functions can have 0, 1, or 2, and it's a degree 2. And then our cubic function, which is a degree 3, can have 1, 2, or 3 x-intercepts. So the degree of the function is actually related to the number of x-intercepts, or the number of zeros we have. Let's go look at that in our notes. So the degree tells us the maximum number of x-intercepts that that function can have. It says the function f of x has at most n x-intercept when n is the degree. If you have a cubic function, you can expect at most 3 x-intercepts. When you have a quadratic function, you can expect at most 2 x-intercepts, and a linear function has at most 1 x-intercept. How is the degree of a polynomial function related to the number of turning points? Well, remember, a turning point is when our graph goes from increasing to decreasing or decreasing to increasing. Let's go and have a look at that on our graph sheet. In general, linear functions have no turning points. Quadratic functions, you can see they have one turning point at that vertex where it goes, right? If you look at this one, it's going from increasing, going up, and then it turns around and comes back down. So that's one turning point. Can do the opposite here where we're going from decreasing. There's our turning point back to increasing. So they have one turning point, but then cubic functions, this one has 2 turning points, this one has 2 turning points, but this one looks like it only has 1 visible turning point. This one has 2 turning points as well. So does it in fact have that cubic function have? Well, let's see. It goes down, and then it actually does change direction there. So there's 1 turning point, and there's another one. So that actually in fact has 2 turning points as well. So if you know the degree of the function, cubic is 3rd degree, quadratic is 2nd, and linear is 1st degree, well, the number of turning points is going to be 1 less than the degree. So linear is 1st, 1 minus 1, that's 0, so it has none. Quadratic is 2nd, minus 1, that means it has 1 turning point. Cubic is 3rd, minus 1, it has 2 turning points. The graph of a polynomial function has only smooth turns. The graph has at most n minus 1 turning points, where n is the degree. Turning points are turning points are points at which the graph changes from increasing to decreasing or vice versa. So again, this is linear, so there's no turns. Quadratic, 1 turn, and cubic, and it has 2 turns. Number 6. How can you predict whether a quadratic or cubic function has a maximum or minimum? We know from previous experience, if a graph opens up and it's quadratic, such as this one and this one, it's going to have a minimum. Whereas if the graph opens down, like this first one, it's going to have a maximum. And in our equation, we can see if a graph's going to open up or down because of that sign in front of the leading coefficient. If the sign in front of the leading coefficient is positive, we know it's going to have a minimum because it opens up. If the sign in front is a negative, then we know it's going to have a maximum because it opens down. That's quadratics. But what does that mean for cubic functions? Well, let's have a look at their leading coefficients. Well, this one, these first two are negative. Okay, so if they're negative, what does that mean in terms of our function? Well, we already know that if it's negative, that means that it's going to fall to the right. Well, that also tells you where those bumps or relative maximums and minimums will be. If it's positive, if the leading coefficient is positive, then it's going to rise to the right. And that also means you're going to have a minimum in that part of the graph. Because if it's rising to the right, it's coming away from a minimum. If it's falling to the right, then it's coming away from a maximum. Quadratic functions have a maximum or minimum value. If the graph of the function opens upward, the function has a minimum value. If the graph of the function opens downward, it has a maximum value. Cubic functions have neither a maximum or minimum value, but they may have relative maximum or a relative minimum value over specific domains. So you can see with the positive x cubed, we're rising to the right, negative x cubed, we're falling to the right. Now that we've gone through these characteristics in more detail and have summarized some information about patterns that we can see with even functions and odd functions, what we know about the degrees of the functions just by looking at the equations and not necessarily graphing them, we can answer different types of questions. The next three examples take advantage of those characteristics and actually ask you to use these without putting them into your calculator. So let's try these out. Example 1 says, determine the following characteristics of each function using its equation. So not your calculator, just its equation. Let's try this out. If I take a look at example 1a, it says f of x is equal to 3x minus 5. Let's figure out all these characteristics. So first of all, the number of possible x-intercepts. Well, I can see it's a degree 1, so I can have 0 or 1 x-intercept, but it's not a constant, so this is going to be 1 x-intercept. I don't know what it is, but I know that there's 1 without doing any math, right? The x-intercept I can identify right from the equation is negative 5. I know that because that's the constant in the function. We talked about that's what that means. The end behavior here, because it's a positive leading coefficient, I've got a plus 3x, right? Plus 3 in front of the x. I know that it's going to be rising to the right. So down to the left and up to the right. Well, knowing that will help me with my domain, because that means that my domain goes from negative infinity to infinity, and my range also goes from negative infinity to infinity. And lastly, the number of possible turning points, well, we know that that's n minus 1 when n's the degree. This is a degree 1, so, and it's a linear equation, so we know that there are no turning points. Okay, let's try this with b. b, I can see, is a second degree function, negative 2x squared minus 4x plus 8. Second degree, so the maximum number of x-intercepts it can have, well, it can have either 0, 1, or 2 x-intercepts, right? Because the maximum is related to the degree, degree 2, so at most we can have 2 x-intercepts. I can identify the y-intercept right from the equation. The y-intercept is a positive 8. Don't forget to take the sign in front of it. The end behavior. Well, if this is quadratic, that means the ends are doing the same thing. It's a negative, which means I have a maximum. So that means it's going to be down on the left and down on the right. If they're down on both the left and the right, that means that my domain, okay, well, that's going to be negative infinity to infinity because it's down and out. But my range is going to go from negative infinity to whatever the maximum value is, which I don't know what that is, but it'll be included. So I'm going to put a square bracket around there. And because this is a quadratic, I know that there's going to be one turning point. So again, I'm not using my calculator here. I'm just using the characteristics from my equation to solve what's going on. C, the function is f of x is equal to 2x cubed plus 10x squared minus 2x minus 10. X-intercepts, there's a maximum of 3, so not 0. There are actually, you don't have 0 x-intercepts. Be 1, 2, or 3 x-intercepts. The odd degrees never have cubic functions always have at least one, because linear equations, if there's a constant there, you can have 0 x-intercepts. I was going to summarize that and draw some conclusions, but that's not true for linear. Y-intercept I can see here is negative 10. The end behavior, because it's odd, the left-hand side and the right-hand side are doing different things. So how do I know what's going on? Well, I'm looking at the sign in front of my leading coefficient. It's positive, which means it is rising to the right. So that means it's down on the left and up on the right. My domain goes from negative infinity to infinity, and my range also goes from negative infinity to infinity. Turning points, there are 2 when we're talking about cubic functions. So that's example 1. Let's have a look at example 2. For example 2, it says match each graph with the correct polynomial function and justify your reasoning. I'm going to ask you to do this one on your own, and then we'll go over it together in class. And if you look at example 3, we're going to do the same thing for that one. It says sketch the graph of a possible polynomial function for each set of characteristics below. What can you conclude about the equation of the function with these characteristics? So they're giving us characteristics, but they're not actually telling us what it's going to look like except for those characteristics, and you're going to draw a graph from that. Before you try this, for A, the range here, another way of writing that range would be from -2 to infinity. So again, you need to be able to read something like that. Whereas for B, they're giving us a range that says y belongs to all the real values from -infinity to infinity. So I want you to try those 2 other examples out, and we're going to go over those together in class. Thanks for joining me today.